It's about a 4,000 meter drop off. This might be related to the eastern hotspot, elevating the temperatures and mantle material here to rise. One last thing before I skip ahead here. There's some large faults on this side, and it showed somewhat of a circular nature and a lot of what looks like compressional ridges to the north and south. And we also see a ridge that looks like it propagated southward. We'll look at this southern ridge tip a little bit later. So Roger Searle went on a cruise and collected these data around the eastern microplate. This is Gloria side-scan sonar. It's a 6 kilohertz system. And the light returns are areas that have low backscatter, usually implying some kind of sediment that's absorbing the sound. And so these dark areas represent areas that are probably lava flows or recent flows. And this suggested that the edges of the microplate were still active today. Additional dredging confirmed that. So in '91, I published a paper that led Jean Franchetot to invite me, Roger Searle, and Richard Hay to go on a cruise with him to take the submersible to investigate an area in Peter Deep we thought might be a brand new spreading axis forming. There were 20 other sites around the microplate that we did. It was really a campaign-style project. We looked at the Peter Deep, and I did my first dive right here on top of the Peter Seamount where I found a black smoker. Since then, in 2017, Jeff Gee and others have gone back and found about another 20 or 30 black smoker hydrothermal vents on the backside of this volcano. This volcano seems to be split, and a new spreading center appears to be forming in here. Backscatter suggests it's all new lava flows. You can see Abyssal Hill fabric coming this way, and then it curves and goes off in this direction. You can't see it that well, so let's get a better image from multi-beam. And you can see the Abyssal Hill fabric curving right through here and coming out the other side. And this rift tip is now cracking through and exposing all the edges of the oceanic crust, showing sheeted dike complex, which you can't normally get to unless you have this type of exposure. So I've digressed somewhat talking about one aspect of the microplate, but the overall picture is that this entire large area, once it's 300 kilometers across, now starts acting like a rigid body. That active transform shear, then the smaller offsets for propagating rifts, gets to a point where it becomes rigid. So the next obvious question is, what is that point? And I'll get to that in just a sec. I just wanted to point out that Hans Schouten at Woods Hole noticed this pattern I just showed you and said, wow, this must be ball-bearing tectonics, where this is an edge-driven project where the plate sliding this way and this way causes the microplate to rotate, like a ball bearing in between the two. So getting to the size of the rigidity, initially it was thought to be here. When one looks at a propagating rift to the south of the microplate I mentioned before at 29 south, it gets down through here. The offset there is about 90 kilometers. The backscatter suggests active lava flows along both limbs. This is a modeling that Jun Korinaga did with Richard Hay. And the question that resulted from this was, is this rigid or is it still shearing? We think that this is at the point now where the earthquakes are showing up more. Well, let me just back up. We think this is a transitional period between deformation and it being rigid. And so instead of being out here, we think the rigid shear transformation boundary is somewhere close to 10 to the 4th kilometers squared. Microplates have played an important role in propagating rifts as well. They all seem to be linked together. Throughout the South Pacific, Eakins and Lonsdale's in 2003 showed this patchwork, like a quilt work along the Pacific Cocos-Nazca plates, where these microplates are existing. And you can see them pretty well in the altimetry as well. And this is an old version of altimetry. The more recent gravity models that Sandwell published are even more accurate. Propagating rifts also appear to play a role in maintaining a ridge axis to touch the other two ridge axes at a ridge triple junction. So at these triple junctions, this rough, smooth boundary that you see here is also related to a propagation of the ridge. There's also a little microplate here called the Galapagos microplate. They seem to like these triple junctions. So in my title of my talk, I mentioned that we go from back arc basins to continental breakup. There's back arc basin examples in Fiji, Woodlark Basin, Lao Basin, Philippine Basin, propagating rifts occurring. And if we look at continental breakup, we can see that there's evidence that occurred in here in the Gulf of Aden and the Red Sea. McGinty published a paper, structural analysis of what he thinks is going on between Ethiopia and the structural elements that are occurring due to this rift propagation, where it's breaking up the continent and creating seafloor spreading. Vink in 1982 also pointed out that before you can have seafloor spreading, you have to thin the lithosphere thin enough to allow seafloor spreading to form. And so that would predict that the entire margin would be stretched to some point, except for where it maybe initially cracked thin, that when you bring it back together, it should have a great deal of overlap. And this is where he modified the Bullard et al.'s 1965 fit of Africa and South America to show complete overlaps, because there shouldn't be any gaps due to the model he proposed. And finally, propagating rifts tend to be quite often associated with hotspots. You can see some great examples of the Iceland hotspot, where you have these V-shaped patterns of ridges propagating southward. And in detailed analysis of the magnetics, they also propagate back up, back and forth. And Martinez and Hay in 2017 published a slow dueling propagation model and proposed a new buoyant mantle propagation model. This is more about mantle dynamics. So, in summary, I want to make sure to finish on time here, because I have two quick little videos I want to show you. It only last 10 seconds. Propagating rifts are extensional plate boundaries that gradually break through lithospheric plates. That's the basic function that they serve. They occur over a wide range of scales in various tectonic settings with various driving mechanisms. The microplate rotating, for example, is one of the mechanisms that causes rifts to propagate. Propagation and spreading combine to produce characteristic V-shaped wedges of lithosphere, and the rift propagation is a primary mechanism that reorganizes the Earth's accretionary plate boundaries. And as I alluded to in the title, these rifts permeate the Pacific, Atlantic, and Indian Oceans, and they're associated with triple junctions, hotspots, and microplates, back arc basins, and continental breakup. Now, one place I didn't talk much about, it was the Atlantic Ocean. Kleinrock published some papers there showing some rift propagation there as well. And, of course, the Iceland hotspot I just showed you. Okay, so these physicists at Cornell, Richard Katz and Eberhard Bodenschatz, built a wax tank because they're interested in the physics of wax. And when they did this, they illuminated the wax from below, very fancy apparatus. They tried to use our wax, but Shell changed the way they make it, so they used a different type of wax that required, they created these microplates in the wax. And it was so similar to what we were seeing in the magnetic anomaly data and the bathymetry that they published a paper on this, and I'll show you some videos from their work. What happened to my videos? They're all gone.
Oh?
Well,
right click.
no, the other one's gone. Well, I'll play it again. There it is. Okay, great.
Yeah, right.
All right. So, real quick. This is two plates moving up and down the page. The black line is a spreading center. This hard-to-see line is a transform fault, and there's one over there. And Bird and Naar in 1984 suggested a mechanism that these things occur. Play again real quick. There we are. That microplates get caught in the shear couple between the transform fault or even small propagating rifts and expand into these rotating microplates. And then the other one, right click. I need a new mouse. Okay. And the other one is this one here. And here's an example of microplates forming without transform faults and forming these characteristic rotated cores that you saw in the Gloria side scan sonar and the bathymetry and magnetics. I'll show that one more time and then I'll end for questions, if I can get there. So you can see the pseudofaults, these angular features as well. And it appears that one microplate is a kernel for the next one. They initiate the new ones. Okay, that's it for me. I stayed under my 25 minutes because we had a late start. Any questions?